In this notebook, in Part 1 of the MLOps Crash Course, we learn how to make machine learning projects production-ready. We begin with Chapter 1, covering what MLOps is, its lifecycle, key tools like Git, Docker, DVC, MLflow, and Kubernetes, and how to set up our environment and project structure. Chapter 2 focuses on data management, using DVC for version control, building reproducible pipelines, checking data quality, and handling large datasets. In Chapter 3, we track experiments with MLflow, log metrics, and store model artifacts for easy comparison. Chapter 4 teaches model packaging, building fast API or Flask inference services, and Dockerizing them for deployment. Finally, Chapter 5 introduces CI/CD for machine learning, using GitHub Actions to test, train, and deliver APIs automatically. By the end of Part 1, you'll know how to version, track, package, and deliver machine learning models efficiently. Chapter 1, Introduction and Setup. What is MLOps? MLOps stands for Machine Learning Operations. It is the bridge between data science and software engineering. In traditional machine learning, models are often built in notebooks and rarely make it into production. MLOps solves this gap. It applies the proven practices of DevOps, like automation, testing, and continuous delivery, to machine learning systems. In MLOps, we treat models just like code. We version them, test them, and deploy them automatically. The goal is to make machine learning workflows repeatable, reliable, and scalable. It also promotes collaboration between data scientists who build models and software engineers who deploy and maintain them. In short, MLOps brings structure, automation, and discipline to the messy world of machine learning development. Why MLOps is important. Let's talk about why MLOps is so important. Without MLOps, teams often face chaos, manual steps, inconsistent environments, and forgotten model versions. It becomes difficult to reproduce results or even know which model is currently running in production. MLOps fixes these issues by automating every stage, from data collection and model training to deployment and monitoring. It reduces manual errors, speeds up delivery, and ensures consistency. Versioning keeps track of every model and dataset change, just like Git tracks code. Scalability is another benefit. MLOps pipelines can automatically handle large workloads and adapt to real-time data. Finally, it enables continuous improvement through feedback loops, so models can retrain and evolve with new data. In summary, MLOps is what transforms experimental models into reliable business solutions that can run and scale in production. MLOps Lifecycle Overview. Stages. The MLOps lifecycle describes how machine learning models move from idea to production and how they keep improving over time. It starts with data collection and pre-processing. This is where we gather raw data, clean it, and transform it into a usable format for training. Next, we move to model training and evaluation. Here, data scientists experiment with algorithms and parameters to build accurate models, and then evaluate them using validation metrics. After that comes model packaging and deployment. This step turns the trained model into a production-ready service, usually wrapped in an application or container. Once deployed, we enter the monitoring and feedback phase. This is where performance is tracked to detect issues like model drift, data changes, or degraded accuracy. When performance drops or new data becomes available, we move to retraining and versioning. New versions of the model are trained, validated, and deployed using automated pipelines. Finally, all these steps work together to enable continuous delivery of models, ensuring that the system always runs the best version available. MLOps Lifecycle Overview. Continuous Loop. The MLOps lifecycle is not a one-time process. It's a continuous loop. Every time new data arrives, or the business environment changes, models may become outdated. MLOps systems detect this automatically and trigger retraining workflows. Automation connects all stages, from collecting new data to retraining and redeploying updated models. This keeps machine learning systems fresh, accurate, and aligned with real-world conditions. Feedback from monitoring tools plays a key role here. If performance metrics drop, the system can alert engineers or even start retraining automatically. Reproducibility is also vital. We must be able to trace every experiment, dataset, and model version. This ensures transparency and allows teams to understand exactly how a model was built. In short, MLOps is not just about building models once. It's about continuously improving them in an automated and reliable way. Tools Overview. Core Tools. Let's look at the main tools used in MLOps. MLOps depends heavily on automation and collaboration, and these tools make that possible. Git is the foundation. It handles version control for code, configurations, and scripts. It keeps your project organized and allows collaboration through platforms like GitHub or GitLab. Docker is next. It solves the problem of "it works on my machine." With Docker, you can package your code, dependencies, and data and environment into a single container. This ensures your model runs the same everywhere, from a laptop to the cloud. DVC, MLflow, CI/CD, and Kubernetes build on these foundations. Together, they handle data management, experiment tracking, deployment, and scaling. We'll now go through these tools step by step to understand their roles in the MLOps pipeline. Tools Overview, DVC and MLflow. Let's start with DVC, or Data Version Control. DVC works like Git, but for large datasets and model files. Instead of storing heavy data directly in Git, DVC stores lightweight references that point to data stored elsewhere, such as cloud storage. This makes it possible to version datasets, reproduce experiments, and keep your data pipeline consistent. It also integrates directly with Git, so you can version your data and code together. Now, MLflow is another key tool in MLOps. It tracks experiments, including parameters, metrics, and artifacts. When you train multiple models, MLflow helps you compare results and select the best one. It also stores trained models in a model registry and can deploy them directly to production using its built-in serving tools. In short, DVC ensures data and model reproducibility, while MLflow ensures experiment tracking and deployment consistency. Tools Overview, CI/CD, and Kubernetes. Now let's look at the last two major tools, CI/CD and Kubernetes. CI/CD stands for Continuous Integration and Continuous Delivery. It automates testing, building, and deployment of machine learning pipelines. Whenever you push new code or a new model version to Git, CI/CD tools like GitHub Actions, GitLab CI, or Jenkins automatically test it and deploy it. This keeps production systems up to date with minimal human intervention. Kubernetes, often called K8s, is a container orchestration platform. It manages how multiple containers run across servers or cloud machines. In MLOps, Kubernetes is used to scale model inference, schedule training jobs, and ensure high availability. When combined with Docker and CI/CD, Kubernetes gives you a full production-grade infrastructure that can handle complex machine learning workloads. In summary, Git and Docker provide the foundation. DVC and MLflow manage data and experiments, and CI/CD with Kubernetes automate deployment and scaling, forming the complete MLOps toolchain. Environment setup and project structure. Before building any MLOps project, we need a clean and consistent environment setup. First, always use a virtual environment, either Venv or Conda. This isolates your dependencies, so different projects do not interfere with each other. Next, pin your dependencies in a requirements.txt or environment.yaml file. This makes sure everyone on the team and every deployment environment uses the exact same library versions. For complete consistency, use Docker. Docker lets you package your environment, including Python version, libraries, and system dependencies inside a container. This guarantees that your code runs exactly the same in development, testing, and production. Environment variables are also important. Store secrets such as database passwords or API keys using .env files or secure managers, instead of hard-coding them in your scripts. Finally, always design for reproducibility. Anyone should be able to recreate your setup and reproduce your results with just a few commands. Here are terminal commands to show how you set up your environment step by step. We first create a virtual environment and activate it. Then, we install the required packages such as NumPy, Pandas, scikit-learn, MLflow, and DVC. Next, we export the installed dependencies to a requirements.txt file. This ensures anyone can recreate the same environment by installing from that file. Finally, we use Docker to build a reproducible image. The output message confirms that our Docker image, named MLOps-env, has been successfully built. With this, your MLOps environment is isolated, consistent, and ready for deployment. Project structure. A well-structured project keeps your MLOps workflow clean and scalable. Let's break down a common structure. The data folder stores raw and processed datasets. The SRC folder contains all source code for pre-processing, training, and evaluation. The models folder holds trained model files or checkpoints. The notebooks folder is for exploratory experiments and research work. The configs folder keeps configuration files, such as YAML settings for pipelines or hyperparameters. The dvc.yaml file defines data and pipeline stages if you're using DVC. And finally, the requirements.txt file lists all dependencies for easy setup. Keeping this structure modular helps with version control, collaboration, and automation in CI/CD pipelines. In the example, at the top level, we have the project folder named MLOps_project. Inside it, the data folder has subfolders for raw and processed datasets. The SRC folder contains scripts for pre-processing, training, and evaluation. The models folder stores serialized model files such as best_model.pkl. Jupyter notebooks go into the notebooks folder, and configuration files such as params.yaml live inside the configs folder. The dvc.yaml file defines data and pipeline stages for DVC. Finally, the requirements.txt file lists dependencies, and the readme.md file documents the project. This structure separates responsibilities clearly, making the project easy to manage, scale, and automate. Chapter 2: Data Management. Data version control with DVC. Let's start with one of the most powerful tools in MLOps, DVC, which stands for Data Version Control. DVC extends Git for managing large datasets and machine learning models. Where Git struggles with big binary files, DVC handles them easily by using lightweight pointers to external storage locations. It lets you version datasets, models, and even pipeline stages, all while staying fully integrated with Git. With DVC, every experiment can be reproduced exactly. If you roll back to a previous Git commit, DVC will automatically restore the corresponding dataset and model version. This brings reproducibility, traceability, and team collaboration to data workflows, something that's hard to achieve with plain Git alone. It also integrates seamlessly with cloud storage providers like AWS S3, Google Drive, or Azure Blob Storage. In short, DVC helps you manage your data with the same precision and reliability that Git brings to code. Here's how DVC works step by step. First, we initialize DVC in the project using the command dvc init. This creates a hidden folder named .dvc which stores configuration files that DVC needs to manage data and pipelines. Next, we use dvc add_data/raw/dataset.csv. This command tells DVC to start tracking that dataset file. But instead of keeping the actual data in Git, DVC creates a small text file called dataset.csv.dvc. That file stores metadata, such as the file checksum and location of the real data, so DVC knows exactly which version belongs to each experiment. Now, notice the next command, git add data/.gitignore dataset.csv.dvc. Here's why this is important. When we ran dvc add, DVC automatically updated the data/.gitignore file. That file tells Git to ignore the large dataset so it doesn't get uploaded into the Git repository, which would slow everything down. So by adding both data/.gitignore and dataset.csv.dvc to Git, we're telling Git to track the small pointer file and the updated ignore rules, but not the heavy data file itself. Then we commit these changes with a message that says, track dataset with DVC. This saves our DVC tracking setup in version control. Next, we connect DVC to remote storage, for example, Google Drive, an S3 bucket, or any other supported cloud. In this example, we use the command dvc remote add-d gdrive gdrive://my-project-storage. The -d flag means set this as the default remote. Finally, we run dvc push to upload the actual dataset to the remote storage. The output confirms the upload by saying, data pushed successfully to G drive. From now on, any team member can clone the project and simply run dvc pull to download the same dataset version. This keeps data and experiments synchronized without bloating the Git repository. In short, dataset.csv.dvc is the lightweight tracker file, and data/.gitignore prevents large data from entering Git. Together, they make DVC efficient and perfectly compatible with version control. Let's talk about data pipelines and why reproducibility is crucial in MLOps. A data pipeline is a sequence of automated steps that transform raw data into trained models and final predictions. Each stage, like pre-processing, training, or evaluation, depends on specific inputs and produces outputs. Without pipelines, data scientists often run scripts manually, making it hard to reproduce results or share consistent experiments. That's where DVC pipelines come in. With DVC, you define each step using a YAML file that specifies what script to run, which files are used, and what files are generated. DVC tracks the relationships between inputs and outputs. So if one file changes, for example, new data arrives, only the necessary stages are rerun automatically. This not only saves time, but also guarantees reproducibility. Anyone can run DVC repro and reproduce the same experiment results, because all dependencies and outputs are versioned and tracked together. In short, data pipelines turn machine learning workflows into reliable, automated systems that can be rerun and audited anytime. Here's how we build a reproducible pipeline using DVC. We start by creating a stage for data preprocessing. The command dvc stage add-n preprocess adds a new pipeline stage named preprocess. We then specify dependencies using the -d flag. These are the input files or scripts that the stage depends on. In this case, the dependencies are src/preprocess.py and data/raw/dataset.csv. Next, the -o flag defines the output, what this stage produces. Here, it's data/processed/clean_data.csv. Finally, after those flags, we include the actual command that should run. Python src/preprocess.py data/raw/dataset.csv. data/processed/clean_data.csv. This means DVC will execute the pre-processing script using the raw dataset as input and store the clean data as output. Next, we create another stage for model training with the name train. It depends on the clean dataset and produces a model file named model.pkl. After setting up both stages, we can run dvc repro. This command reproduces the full pipeline from start to finish. If nothing has changed since the last run, DVC will skip steps automatically to save time. But if new data is added or a script changes, DVC detects it and reruns only the affected stages. The output shows each stage running in sequence and finishes with pipeline completed successfully. This approach guarantees that every result is traceable and reproducible. It also helps teams collaborate confidently, knowing that everyone can reproduce the exact same pipeline and results at any time. Data validation and schema checks. In MLOps, data validation and schema checking are essential for keeping models reliable and stable. Even a small change in the dataset, like a missing column, wrong data type, or new category, can silently break a trained model. That's why we perform data validation before every training run. Data validation checks for common issues, missing values, invalid ranges, incorrect data types, and unexpected categories. To formalize this process, we define a schema, a clear description of what each column should contain. The schema lists column names, data types, allowed ranges, and whether null values are acceptable. If incoming data doesn't match the schema, the validation step raises an alert or fails the pipeline, stopping bad data from reaching the model. Popular tools for this include Pandera for Python-based validation, Great Expectations for flexible data checks, and TensorFlow data validation, also known as TFDV for TensorFlow pipelines. Here's a simple example of performing schema checks using the Pandera library. We first import pandas and Pandera. Then we define a schema using DataFrame schema. This acts as the rulebook for our dataset. The schema specifies 3 columns: age, income, and city. The age column must be an integer and must fall between 0 and 120. The income column must be a floating point number greater than or equal to 0. The city column must be a string and cannot contain null values. Next, we create a sample data frame with some invalid data. Notice that one age is negative and one city value is missing. Finally, we run schema.validate to check the data. Pandera automatically scans every column and raises a clear schema error when something doesn't meet the rules. In the output, you can see 2 errors. One for the age column, because -5 is outside the valid range, and one for the city column, because it contains a null value. This process allows your pipeline to fail fast, stopping early before training begins. That means your model never learns from broken or inconsistent data. By integrating schema validation into your MLOps workflow, you ensure that every model version is trained on trustworthy, high-quality input data. Now let's see how to actually run this schema validation step inside an MLOps workflow. First, this is a Python script, not a DVC command. You'll typically save this code in a file named something like validatedata.py. If you're using DVC pipelines, this script becomes one stage of your pipeline. For example, a validation stage that runs before training. You can define that stage in your dvc.yaml file, like this. Then you can run the validation automatically using dvc repro, which means DVC will execute the validation stage whenever the dataset changes. Managing large datasets in teams. In most machine learning projects, datasets quickly grow to gigabytes or even terabytes. Storing those large files directly in GitHub is not practical. It slows everything down and can even break the repository. That's why teams use DVC remote storage. The idea is simple. Git tracks code, small configuration files, and DVC metadata, while DVC handles the large data files in external storage like Amazon S3, Google Drive, or an Azure Blob. Here's how it works in a team environment. Each teammate has the same Git repository, but the data files themselves are not inside Git. They live in a shared DVC remote. When someone updates or adds new data, they use DVC push to upload it. Other teammates can then run DVC pull to download that same version locally. This keeps everyone synchronized. No more missing data file errors, and no more sending datasets through chat or email. You can even set up multiple remotes, for example, one remote on Google Drive for shared storage and another on S3 for backups. In short, Git stores the version control history. DVC stores the actual data. Together, they ensure that everyone in the team always works with the exact same version of both code and dataset. That's the foundation of scalable, team-friendly machine learning development. Let's walk through how a team would actually use these commands. First, everyone starts by cloning the shared Git repository using git clone followed by the repository URL. Then they move into the project directory. Next, they run DVC pull. This downloads the dataset from the shared DVC remote, so everyone now has the same version of the data on their local machine. When someone updates or pre-processes the data, they might run a Python script like preprocess_data.py. This script produces a new dataset, for example, clean_data.csv. To start tracking this new file, we use DVC add data/processed/clean_data.csv. This creates a .dvc metadata file and updates the ignore rules. Next, we commit those changes to Git using git add data/.gitignore data/processed/clean_data.csv.dvc followed by git commit-m update cleaned dataset. Finally, the updated dataset version is uploaded to remote storage using DVC push. The terminal confirms the upload with a progress bar and a message that says, "Data pushed successfully to remote." Now every teammate can simply pull that update and continue working. No data duplication, no broken paths, and full traceability of which dataset version was used for which model. This is how professional machine learning teams manage large datasets safely, efficiently, and reproducibly. Chapter 3: Experiment Tracking. Experiment logging and comparison. In real-world machine learning projects, you often run dozens, sometimes hundreds, of experiments. Each experiment might use a slightly different dataset split, model configuration, or hyperparameter setting. Without proper tracking, it becomes impossible to remember which run produced the best result. That's where experiment tracking tools come in, and one of the most popular is MLflow. MLflow lets you record all the important details of each experiment, like parameter values, metrics, and even the model artifacts. These results are stored in a local folder or remote tracking server, so you can later visualize and compare them side by side in a web dashboard. The goal is reproducibility. If a teammate wants to reproduce your best run, they can simply pull the exact parameters and model version from the MLflow log. No guesswork needed. In short, experiment logging helps you answer questions like, which hyperparameters gave the highest accuracy? Did the model improve after adding new data? Which model version should go to production? Let's look at a simple example. Here's how to use MLflow for experiment tracking in practice. Let's walk through what it does. First, we import MLflow and scikit-learn libraries. we use the classic iris dataset for demonstration and split it into training and test sets. Inside the block with MLflow.start_run, we start a new experiment run. The run name, random forest _experiment, will appear in the MLflow dashboard. Then, we train a random forest model with 100 trees. After training, we make predictions and calculate the model's accuracy. Now, the key part, we log the parameters, metrics, and the trained model itself using MLflow functions. The function log_param records the hyperparameter used. Log_metric saves the accuracy, and log_model stores the trained model artifact. Once this script finishes running, you can view all results using the command MLflow UI. This opens a local web dashboard, usually at the address localhost:5000. There, you'll see every experiment run, with side-by-side comparisons of accuracy, hyperparameters, and models. You can sort by metrics to find the best performing model instantly. This makes collaboration and debugging much easier, because every experiment is automatically documented. In summary, MLflow turns your experiments into a searchable record of progress. Every run, every parameter, every model, all versioned and reproducible. MLflow tracking basics. Let's look deeper at how MLflow actually tracks your experiments. MLflow organizes everything into experiments and runs. An experiment is like a project folder. It holds all related training attempts. Each run inside that experiment is a single model training session, with its own parameters, metrics, and saved model. When you start an experiment with MLflow.start_run, MLflow automatically creates a folder named MLruns. In your project directory, inside it, you'll see numbered folders. Each one is a different experiment run. Each run folder contains a text file with parameters, another with metrics, and an artifacts folder where the model and outputs are saved. You can open the MLflow web interface using MLflow_UI, and you'll see all runs displayed under their experiment names. From the UI, you can compare model performance, download artifacts, reproduce the exact setup of any past run. Parameter and metric management. In MLflow, we use parameters and metrics to keep track of how each run was configured and how well it performed. A parameter is any setting or hyperparameter you pass into your model. For example, the number of trees or the learning rate. To log one parameter, write MLflow.log_param. This saves the parameter value to that specific run. If you want to log multiple parameters at once, use MLflow.log_params. Metrics, on the other hand, are numeric results that measure performance, like accuracy, loss, or F1 score. To log a metric, use MLflow.log_metric. You can log updated metric values during training, and MLflow will plot how they change across epochs or steps. After running experiments, open the MLflow UI. There you can compare parameters and metrics across runs in the same experiment. This helps identify which settings produce the best results. Finally, you can retrieve all the information for a specific run programmatically with MLflow.get_run. Inside parentheses, run_ID. This makes it easy to reproduce your best run anytime by reading the stored parameters and artifacts. Here's how to understand what's happening in this code. First, we explicitly tell MLflow where to save experiments using the command MLflow.set_tracking_URI file:/MLruns. That ensures the tracking data stays inside our project folder. Then, we define or select an experiment with MLflow.set_experiment, open parenthesis, experiment_name, close parenthesis. If it doesn't exist, MLflow automatically creates it. Next, inside the with block, we start a run named run_1. We log a parameter, a metric, and even a local file, in this case, the requirements text file, to show that artifacts can include any file, not just models. After the run finishes, we call MLflow.get_experiment_by_name to print metadata such as the experiment ID and artifact path. The printed ID corresponds to a folder inside the MLruns directory. That folder contains all your experiment data, parameters, metrics, and model files, organized neatly for reproducibility. When you run MLflow -UI, you'll see this experiment appear in the dashboard. Each run will display its accuracy, parameters, and artifact links. This is the foundation of MLflow tracking, a simple but powerful structure that records every experiment detail automatically so you can focus on improving the model, not managing logs manually. Model artifact storage. After training a model, we usually want to save it, not just the weights, but also everything needed to reproduce that run later. In MLflow, saved files are called artifacts. Artifacts can include your trained model, plots, or configuration files. When you finish training inside a run, call mlflow.sklearn.log_model. Inside parentheses, model. This saves the model as an artifact under the current run folder. MLflow automatically organizes these files inside MLruns/experiment_ID/run_ID/artifacts. That means every run keeps its own saved model, so you can revisit or compare them later. You can also load a model back using mlflow.sklearn.load_model, followed by the model's run path. For example, runs:/your run_ID/model. This lets you quickly reload and reuse a previously trained model without retraining it. Artifacts are also visible in the MLflow dashboard. In the user interface, open your experiment and click a run. You'll see an artifacts section that lists saved model files. You can download or inspect them directly from there. This makes experiment management fully reproducible. Everything from parameters to trained model files stays linked inside one run folder. Chapter 4: Model Packaging. Environment reproducibility. In MLOps, environment reproducibility means being able to rebuild the exact same setup that produced a model. Same library versions, same dependencies, and same configurations. Without this, a model might work perfectly on your laptop, but fail when deployed on a server or in the cloud. That's what developers call the classic works on my machine problem. To solve this, tools like MLflow automatically capture your environment when you log a model. When you save a model using mlflow.sklearn.log_model, it also creates a conda.yaml file or a requirements.txt file inside the artifact folder. This file lists all the dependencies, such as scikit-learn, numpy, and pandas, with exact version numbers. Later, anyone can reproduce the same environment by using that file to recreate a matching setup. You can also define your environment manually using a requirements.txt file or a Docker file. Docker is especially popular in MLOps because it lets you package everything, code, data, and dependencies, into one portable container image. In short, reproducibility ensures that if a model ran once successfully, it can run the same way, anywhere, at any time, by anyone on your team. In this Docker file, we start from the official Python 3.10 Slim image. That gives us a lightweight but complete Python environment. Then we set our working directory inside the container to /app. Next, We copy our source folder and the requirements.txt file into that directory. The run command upgrades pip and installs all the dependencies listed in requirements.txt. This ensures the container has the exact same package versions every time it runs. Finally, the CMD instruction tells Docker which command to execute when the container starts. In this case, running our training script inside the source folder. Now let's look at the requirements.txt file. It pins every dependency version explicitly. For example, we specify MLflow version 2.4.0, sklearn version 1.2.2, pandas version 2.0.1, and numpy version 1.25.0. Pinning versions like this is critical. It ensures that the training environment today will be identical to the one your teammate or CI system uses tomorrow. With those files ready, we move to the terminal. First, create an ML runs folder on your host machine. This is where MLflow will store experiment logs and artifacts. Next, build the image using docker space build space -t space MLOps -train space dot. The period means the current directory, where the Docker file is located. After the image builds successfully, run the container with docker space run space -- remove space -v space $parenthesis pwd /ml runs :app /ml runs space MLOps -train. Let's unpack that. The -v flag mounts a volume. It connects the ML runs folder from your host into the container's /app /ml runs path. That way, when MLflow logs data during training, those files appear directly in your host system, not just inside the container. A -- remove flag tells Docker to clean up the container after it finishes, keeping your workspace tidy. Once the training completes, you'll have a new folder inside ML runs containing your experiment results and model artifacts. Finally, launch the MLflow interface with MLflow space UI space -- backend -store -URI space file :./ML runs. This command reads the same folder we mounted earlier, allowing you to browse the run results directly in your browser. This workflow represents true environment reproducibility in MLOps. You can share the Docker file and requirements file with your team, and everyone, on any machine, local or cloud, can rebuild the same environment with a single Docker command. That's the key to stable, repeatable experiments and reliable model deployment pipelines. Building fast API/Fast inference service in MLOps. Serving your trained model as an API is a key step. It allows other applications or users to send data and get predictions in real time. Here we use Fast API, a modern Python framework for building fast, production-ready APIs. The workflow is simple. Load the model you saved earlier, either from a file or from the MLflow artifact folder. Define an API endpoint. For example, /predict. Clients send input data in JSON format. Inside the endpoint, call the model's predict method with the input data. Return the prediction as JSON. Fast API automatically generates documentation at /docs. This is very useful for testing your API manually. You can run the API locally using uvicorn app -- reload. The -- reload flag automatically restarts the server when you edit the code, which is handy during development. Once running, you can test the API from a browser or with curl commands. This pattern bridges the gap between training and deployment, turning a saved model into a live service. In this code, we first import Fast API and base model from Pydantic. Fast API is the main web framework, and Pydantic helps us define and validate structured input data, so users can't send invalid or missing fields. Then we define a class named iris_input. This class describes the expected input structure. In this case, 4 numeric fields for sepal length, sepal width, petal length, and petal width. When a request arrives, Fast API automatically converts the JSON body into this iris_input object and also checks that all the values are numbers. This is great for reliability and error handling in production. Next, we create an app instance using app equals fast API title iris classifier API. This single line starts the whole API. You can think of it like creating a small web server object. The title is optional, but shows up in the auto-generated documentation page at /docs. Then we load our trained model using MLflow. Here, run ID refers to the specific experiment run where your model was logged. This command automatically restores the saved model and its environment. In MLOps, this is critical because it ensures the model being served is exactly the same one that was trained and registered. Now we define our API endpoint for predictions using the decorator @app_post/predict. The word post means this endpoint receives data from the client. Right below that, we define a function named predict, which takes one argument, input data, iris input. FastAPI automatically converts the JSON body of the request into this iris input object. Inside the function, we extract the 4 input values, call the model's predict method, and return the predicted class as a JSON dictionary. So every time a client sends input data to the /predict endpoint, the model runs and responds instantly with a prediction. Save this file as src/app.py. Install dependencies by typing pip install fast API uvicorn. Run the API locally using uvicorn src.app:/app/reload. Uvicorn is the name of the ASGI, Asynchronous Server Gateway Interface server, you are running. Uvicorn is a high-performance, lightweight server designed to handle asynchronous Python web frameworks like FastAPI. src.app:/app tells Uvicorn exactly where to find your application instance. --reload is a development flag. It tells Uvicorn to monitor the files in your project directory. If you make any changes to your code, for example in app.py, and save the file, Uvicorn will automatically restart the server, so you don't have to manually stop and start it. Next command uses curl, means client URL, a command line tool, to simulate a user or another application making a request to your API. Curl being executed here. It is used to transfer data with URLs, commonly used for testing APIs. -x post means the HTTP method or verb. Post is used to send data to the server, often to create a new resource or, in this case, trigger a prediction task. Next is the target URL. After that, -h is the curl command line option used to pass a custom header to the server. Content type, application, JSON. This is the actual HTTP header. -d means the data flag. This is the actual data payload, the body of the request sent to the server. The enclosed JSON object contains the 4 required features, sepal length, sepal width, etc., that the /predict endpoint expects in order to run the classification model. In short, this command simulates a request to your server asking the /predict endpoint to classify an iris flower based on the provided measurements. FastAPI automatically provides an interactive Swagger interface where you can test requests visually. This is one of the easiest and most powerful ways to turn any ML model into a real, production-ready API service, and it fits perfectly into the MLOps pipeline right before containerization and deployment. Dockerizing ML applications. In MLOps, Dockerization means packaging your model service and its environment into a single portable container. That container can run anywhere, your laptop, a testing server, or the cloud, and it will always behave exactly the same way. We start with a file called Docker file. No extension, just Docker file. It's basically a set of instructions telling Docker how to build the container image. Let's see what it looks like. Let's explain what happens in this Docker file step by step. We start by pulling a base image, in this case, Python:310-slim. This gives us a clean and lightweight Python environment. Next, we set a working directory inside the container called /app. All the following commands will run inside this folder. We then copy our project files into the container. That includes the Fast API source code in the src folder and the requirements.txt file that lists all our dependencies. Then, we install the dependencies by running pip install -r space requirements.txt. The hashtag #nocachedir flag keeps the image smaller by not storing pip's cache files. After that, we expose port 8000, which is the port where our API listens. Finally, the cmd command tells Docker what to run when the container starts. Here we run uvicorn src.app:app-host 0.0.0.0 -port 8000. This line launches our Fast API service automatically when the container runs. Here is the requirements.txt file, which lists the dependencies our container must install. To build your Docker image, open a terminal in your project folder and type docker build -t -ml-api -dot. The dot at the end means build using the current directory. Once the image is built, you can start a container from it by running docker run -p 8000:8000 -ml-api. This maps port 8000 on your computer to port 8000 inside the container. So you can access the API in your browser at http://127.0.0.1:8000/docs. And that's it. Your model is now running inside a fully isolated container. No matter where you run it, on Windows, Linux, or in the cloud, the behavior will be identical. That's the power of Docker in MLOps. It guarantees reproducibility, consistency, and easy deployment. Chapter 5: CI/CD for ML. CI/CD principles for machine learning projects in traditional software development. CI/CD, which stands for Continuous Integration and Continuous Delivery, is the process of automatically testing, building, and deploying applications whenever new code is added. In MLOps, we use the same principles, but we extend them to include data, models, and experiments, not just source code. Let's break it down. Continuous integration, or CI, means every time someone commits code to the repository, a pipeline automatically runs to verify that nothing breaks. That pipeline usually includes linting, unit tests, data validation, and sometimes even a short model training run. This helps catch issues early, before they reach production. Continuous delivery, or CD, is the next step. It ensures that when your model or service passes all tests, it can be automatically deployed to a staging or production environment. That means no manual steps are needed to roll out new versions of your model or API. In the context of machine learning, CD might mean automatically packaging and deploying your model to a prediction service. For example, your Fast API Docker container, or registering it into an MLflow model registry ready to serve. Here's why CI/CD is so important in MLOps. It ensures reproducibility by always rebuilding the environment from defined dependencies. It ensures consistency by using the same tests and build steps for every change. It ensures speed by automatically deploying successful versions. So instead of data scientists manually training and pushing models, the system handles everything in a structured, traceable way. To make this work, we usually rely on automation tools like GitHub Actions, GitLab CI, or Jenkins. These tools run YAML configuration files that define what steps to perform when code is pushed, merged, or tagged in version control. They can install dependencies, run tests, train models, push Docker images, and even deploy APIs to cloud platforms automatically. In short, CI/CD in MLOps is about automation, traceability, and consistency across code, data, and models. It's what makes modern machine learning production-ready. Every model version, every dataset change, every pipeline update, all tracked, tested, and deployed automatically. GitHub Actions for automation. In MLOps, GitHub Actions is one of the easiest and most flexible ways to automate your workflow. It's built directly into GitHub and allows you to automatically test, train, and deploy your models every time new code is pushed or merged. Let's understand how it works. Every GitHub action starts with a workflow file, a simple text file written in YAML format and stored inside your repository, named MLOps.yml. This file defines when the automation should run, what environment it should use, and which steps to execute. For example, you can make it run automatically whenever someone pushes new code or opens a pull request to the main branch. In MLOps, a typical pipeline includes these steps: set up Python and dependencies, install project requirements, run automated tests or linting, train or validate the model, build and push Docker image, deploy the service automatically. Now let's look at a real example of a GitHub Actions workflow for an ML project inside MLOps.yml. Let's go line by line to understand what's happening here. We start by giving our workflow a name, MLOps pipeline. Under the On section, we define when this workflow should run. Here it's triggered on every push or pull request to the main branch. That means every time someone updates code, this automation will automatically check, build, and even deploy the new version. Then we define one job called build-train-deploy and tell GitHub to run it on an Ubuntu environment. A job is just a collection of steps that run in order. The first step is checkout repository. This uses the built-in GitHub action/checkout, which downloads the code from your repository into the virtual machine. Next, we set up Python using the action/setup-python action and specify Python version 3.10. After that, we install dependencies. This is where we install all the libraries listed in requirements.txt. We use two commands, first to upgrade pip, and then to install all dependencies. The next step runs tests using PyTest. Automated testing helps catch syntax or logic errors before any model is deployed. This is part of the continuous integration phase. Then we run our training script, train.py, which trains the model and logs metrics and artifacts to MLflow. After training, we build a Docker image of our API using the same command we used earlier, docker build-t space ml-api space dot. This prepares the container for deployment. Finally, we push that image to Docker Hub. To keep credentials safe, we store the Docker username and password as GitHub secrets and reference them with $, secrets, Docker username, and secrets, Docker password. This way, no sensitive information is ever exposed in the code. Finally, in the last step, we log in to Docker Hub and push our image. The first command uses Docker login with a secure method. It takes the password stored in GitHub secrets and sends it to Docker Hub through standard input, so the password never appears in plain text. Next, we use Docker tag to rename the local image. It adds the username and the repository name so Docker Hub knows where to store it. For example, we tag our image as username/ml-api:\latest. And finally, Docker push uploads that tagged image to Docker Hub. Once pushed, the image becomes accessible to deploy anywhere. For instance, on cloud services like AWS, GCP, or Kubernetes. This completes the automation loop. After every push, your model is retrained, containerized, and published automatically. Automated testing, linting, and model training. This part of the MLOps pipeline focuses on automation for quality assurance, making sure that every code change, data update, or training script works perfectly before deployment. Let's go line by line. First, ensure code quality before deployment. In MLOps, we never want untested or messy code to reach production. Before a model or service is deployed, we run several automated checks to verify that everything meets quality standards. Next, we run linting tools automatically, such as Flake 8 or Black. These tools check code formatting, indentation, and naming conventions. They don't change how the code works. They simply make it consistent and clean, so the whole team can easily read and maintain it. The best part is, these tools run automatically inside the pipeline, so you never have to do it manually. Then, we execute unit tests for both data and model logic. For example, you might test that your data pre-processing functions handle missing values correctly, or that the model outputs predictions with the right shape and type. These tests catch problems early, before they cause issues in production. After that, we automate a short model training step in the CI pipeline. This training run doesn't use the full dataset. It's a lightweight check to confirm that the training script runs successfully from start to finish. It ensures that recent code changes haven't broken the training logic or pipeline structure. Next, this process prevents broken code or bad models from deploying. If any linting step, test, or training run fails, the pipeline stops automatically. The model won't be built or deployed until the issue is fixed. This keeps your production environment clean and reliable. Finally, we define these tests in a YAML workflow file, for example, in a GitHub Actions or Jenkins configuration. That file tells the automation tool exactly what to do whenever code is pushed or merged. It includes steps for installing dependencies, running linting, running tests, and optionally, training the model. Here's what these steps might look like inside a GitHub Actions YAML file. This workflow file defines how GitHub Actions automatically tests and trains our machine learning project. It lives inside the folder named .github/workflows. Every time we push code to GitHub, this file tells the automation system what to do. It starts by giving the workflow a name, test and train pipeline. Then it defines when the workflow should run. Here, it's triggered automatically whenever code is pushed to the main branch. That means every change gets verified before merging or deployment. Next, we define one job called test-train. GitHub will run this job on an Ubuntu Linux environment. Basically, a clean virtual machine where all steps will be executed. The first step checks out our repository code, so the workflow has access to all project files. Then it sets up Python version 3.10, so every run uses a consistent environment. After that, we install dependencies. The first command installs everything listed in the requirements.txt file. For example, packages like pandas, scikit-learn, or MLflow. The second command installs Flake 8 and PyTest. These are tools used for linting and testing. Finally, the workflow performs a short model training check. It runs the train.py script with one epoch, just enough to confirm that the training code still works correctly. This helps detect script errors early without wasting compute time. So in simple terms, This workflow automatically checks code quality, runs tests, and confirms training works every time new code is pushed. If all steps pass, the project moves forward safely to the deployment stages. That's how GitHub Actions guarantees reliable automation and quality control in MLOps pipelines. Continuous delivery of ML APIs. Continuous delivery is the final stage of the CI/CD process. It's where your machine learning model, or API, is automatically packaged, tested, and deployed whenever new changes are merged into the main branch. Let's go through what each line on this slide means. First, we automate deployment after tests pass. This means our delivery process only runs if all previous stages, like linting, unit tests, and quick model training, succeed. If something fails, deployment stops. That guarantees that only stable builds ever reach production. Next, we use CI/CD to build and publish Docker images. In practice, the pipeline takes the latest version of your model and API, builds a Docker image, and pushes it to a container registry such as Docker Hub or Amazon ECR. This ensures every version of your model is stored in a consistent, reproducible environment. Then, we deploy new model or API versions automatically. Once the Docker image is uploaded, another job in the workflow can pull that image and start it on a cloud service or a Kubernetes cluster. That means as soon as your code is ready, your live API gets updated automatically, no manual steps needed. We can also push to staging or production environments. Staging is used for internal testing, a safe space to confirm everything works. When the checks pass, the pipeline automatically deploys the same version to production. So what you tested is exactly what runs for real users. The next point, ensure reproducible, traceable releases, means that every deployment is linked to a specific Git commit and Docker image tag. You can always trace back which version of the model, code, and data was used for any prediction. That level of traceability is one of the main goals of MLOps. Finally, roll back easily if something fails. Because each release is versioned, you can simply redeploy an older image if a new version causes errors or performance drops. No more rebuilding manually. Just point the deployment system to a previous tag. Together, these principles make continuous delivery reliable and safe for machine learning systems. They allow teams to release updates quickly, test them confidently, and maintain complete control over every version of their model APIs. Thanks for watching.